You sit alone inside a submarine. It isn't made of metal, nor is it powered by nuclear energy. It is simply a small wooden sphere submerged beneath the surface of New York Harbor. Directly overhead, a British warship looms large. Its massive hull has not yet detected your presence. The surrounding ocean presses in from every direction. The space inside is so cramped you can barely move. You pedal a treadle to turn the propeller, inching forward in near total darkness. The air you brought with you is your only supply, and time is ticking away, second by second. You are inside the Turtle, the world's first combat-capable submarine. Its underwater endurance is less than 30 minutes. That is its limit. Your mission is to quietly dive beneath the enemy ship and attach a timed explosive to its hull. It is an audacious plan. But the submarine has no engine, no oxygen system, and not even a targeting device. Ultimately, the Turtle's mission failed. The pilot could not drill into the British warship's hull because it was sheathed in copper. Running low on oxygen, the pilot had to abandon the mission, releasing the explosive harmlessly into the harbor. For the next 2 centuries, navies around the world tried every method imaginable to extend submarine underwater endurance. Hand-cranked propellers, steam engines, diesel-electric systems, chemical scrubbers, but they all faced the same problem. Sooner or later, the submarine had to surface. Until one day, this paradigm was completely shattered. Solving the problem of long-duration underwater endurance changed everything. The role of the submarine became critical. Today, they are not used just to sneak up on ships and plant bombs. They influence global politics and sway national decisions. But before we dive deeper into that, let's reveal the secret that allows submarines to lurk for months at a time. Nearly 2 centuries after the Turtle, the U.S. Navy launched the USS Nautilus. Its power source was neither manpower nor diesel, but a brand new technology, a nuclear reactor. This wasn't just a breakthrough in propulsion, it marked a turning point in naval history. For the first time, a submarine could stay underwater for weeks, not because it could hold its breath longer, but because it no longer needed to breathe. The Nautilus shattered endurance records, crossed under the Arctic ice, and proved that nuclear power was not only feasible but represented the future. It laid the foundation for the development of all modern submarines that followed. But how exactly does a nuclear submarine work? From beneath your feet comes a low humming sound. No louder than a refrigerator, yet it provides all the power for the entire submarine. In the early days of atomic research, scientists discovered that nuclear fission releases immense energy, and this energy can be converted into electricity. For over 70 years, nuclear power plants have used this principle to power homes, cities, and industries worldwide. Similarly, every nuclear submarine relies on its own miniature nuclear reactor on board to generate power. Every atom has a nucleus made of protons and neutrons. The number of protons determines the chemical element. Nuclei with the same number of protons but different numbers of neutrons are called isotopes of that element. Some heavy nuclei are prone to nuclear fission, splitting into 2 lighter nuclei. The total mass of the fragments is less than the original nucleus. This missing mass is converted into energy. The energy released by nuclear fission is enormous. Einstein's famous equation E at mc2 reveals this. Energy equals the change in mass multiplied by the speed of light squared. At the heart of every nuclear submarine is a sealed reactor core. It is shielded to maintain high pressure, designed to last for decades, and operates almost silently. Inside the core, enriched uranium-235 fuel is arranged in a precise grid. It is then bombarded by neutrons. This causes some of the uranium nuclei to fission, split, releasing heat and more neutrons. The newly produced neutrons strike other nuclei, triggering a chain reaction. But this chain reaction must be controlled. Therefore, the fuel rods are surrounded by a moderator, usually water, which slows down the neutrons. Fast neutrons tend to zip past uranium nuclei, while slow neutrons are more easily captured by them. This process keeps the nuclear reaction stable and efficient. The water, heated by the fission, becomes the primary coolant. It circulates under high pressure to prevent boiling, transporting the heat from the core to a heat exchanger. Inside the heat exchanger, the heat is transferred to a separate water system, the secondary loop. In the secondary loop, the water is allowed to boil, turning into high-pressure steam. This steam spins turbines. The turbines, in turn, drive the submarine's propeller and generate electricity for all the ship's systems. Most submarines use pressurized water reactors, PWR. Because they are compact, technologically mature, and highly safe, they have become the industry standard. But pressurized water isn't the only way to cool a nuclear reactor. Some submarines, especially older models or experimental ones, use natural circulation reactors, relying on the basic physics of hot water rising and cold water sinking. There are also liquid metal reactors using liquid metals like sodium or lead instead of water as coolant. Metal conducts heat far better than water, allowing for smaller turbines and more compact reactors. However, the cost is extremely high. Liquid metals, especially sodium, are highly reactive. If they leak and contact air or water, they can catch fire. Furthermore, over time, the liquid metal becomes highly radioactive, requiring extreme sealing measures. Even worse, if the system cools down too much, the metal can solidify inside the pipes, paralyzing the entire reactor. Therefore, despite the advantages of liquid metal reactors, they require extreme precision and are rarely used in frontline naval vessels. This is why most naval reactors choose water as a coolant. It serves as a simple heat transfer medium, a moderator, and a coolant all in one. With this system, a uranium fuel core the size of a large desk can power a submarine for 20 years or more without needing to refuel. As long as the system is running, the submarine can stay underwater for as long as necessary, provided there is enough air supply. We cannot store 3 months' worth of breathable air and fresh water for 100 people. Otherwise, the submarine would just be a floating warehouse. Therefore, the submarine must manufacture these two resources itself. The atmosphere inside a submarine is a precisely designed system, sealed, pressurized, and monitored in real time. Every time a crew member inhales, they consume oxygen. Every time they exhale, they release carbon dioxide. Inside a sealed steel shell, this gas balance is critical. To supply fresh oxygen, submarines use electrolysis to generate oxygen. Seawater is drawn in from outside, filtered, pressurized, and treated to remove particulates. Before entering the electrolysis system, the seawater passes through a series of desalination filters and deionizers to remove salt, minerals, and tiny impurities. The result is pure water, chemically stable and clean, ready for electrolysis. We know that water is made of 2 hydrogen atoms and 1 oxygen atom. An electric current in the electrolysis cell breaks the chemical bonds of the water molecules, splitting them into pure oxygen and hydrogen gas. The oxygen is released into the cabin, mixed into the air supply via the ventilation system. The hydrogen is carefully pumped overboard and thoroughly diluted in the ocean water to prevent the buildup of flammable gas. This is the result of chemical engineering and environmental control working silently together in the deep sea. Additionally, the system must precisely control the voltage, temperature, and salinity of the input water. Otherwise, it could corrode the equipment or even create dangerous gas mixtures. More importantly, the partial pressure of oxygen inside the sub, a key indicator of how efficiently oxygen moves from lungs to blood, must be strictly controlled within a specific range. Too low, and the crew suffers hypoxia, leading to confusion, fatigue, or even coma. Too high, and oxygen becomes toxic, increasing fire risks and causing long-term health issues. Therefore, the oxygen partial pressure in every compartment is adjusted every hour. The submarine can autonomously generate breathable air, but air is only half the requirement for survival. A submarine crew consumes tons of fresh water daily for drinking, cooking, cleaning, and cooling. Carrying such a massive amount of fresh water is obviously impractical. Thus, the submarine also needs to convert seawater into fresh water. Distillation units on board heat seawater to a boil, separating the salt and impurities. The steam cools and condenses into liquid water, stored as drinking water. Some modern submarines also use reverse osmosis, RO technology, using high pressure to force seawater through membranes, filtering out salt at the molecular level. Now, the problems of power, air, and water are solved. But what about food supply? Before departure, every box of rice, every can of beans, and every slice of bread is loaded onto the sub. For a 3-month mission with a crew of 130, this means carrying nearly 20 tons of provisions. Most food is vacuum sealed, dehydrated, or canned. Fresh fruits and vegetables are stuffed into every available corner and are usually finished within the first week of the mission. After that, the crew relies on shelf-stable foods, rehydrated stews, powdered eggs, frozen meats, and enough coffee to keep everyone awake. The submarine's kitchen, known as the galley, is tiny but highly efficient. It operates 24 hours a day. Because the crew works in shifts, some are just waking up while others are going to sleep. Everyone hopes for a hot meal. Storage space on the ship is everywhere, behind walls, under bunks, inside deck compartments. On some submarines, at the start of a mission, even the floor of the torpedo room is stacked high with food crates. At 300 meters deep, there are no supply ships and no emergency takeout. Once the food runs out, the mission must end. Therefore, the ultimate limiting factor for a submarine's underwater endurance is food, not fuel. Imagine living in a place with no windows, no sunlight, no rain, and no wind. Only artificial light, recycled air, and a constant humming sound. This is life aboard a nuclear submarine. For the crew, a long patrol means not seeing the sky for weeks or even months. Outside is lethal water pressure. Inside is psychological pressure. Most crew members work in shifts, following an 18-hour cycle. Sleep, eat, work, repeat. Regardless of whether it is day or night on the surface. Many submarines also practice hot bunking, where one bed is shared by 2 or 3 crew members in rotation. To maintain alertness and morale, daily routine is essential. Exercise bikes and rowing machines are squeezed into corners, mounted on special brackets to reduce noise. The mess hall plays movies via headphones. Birthdays are celebrated with canned cakes and the repetition of familiar jokes. Noise discipline is paramount. A dropped wrench, a slammed hatch, footsteps on the steel hull. Any sound could travel into the ocean and be picked up by enemy passive sonar. There is even an unwritten rule on board. Speak clearly and always know where you are. The crew on board are engineers, electricians, sonar technicians, cooks, medics, and navigators. But they are also psychological support for one another. Teammates are the guardians of each other's mental state. When the outside world vanishes, the only world that exists is the collective space you build together. This forms an ironic contrast with the purpose of nuclear submarines. The nuclear-powered submarine is a key component of the nuclear triad strategy. The nuclear triad refers to the 3 ways a nation can launch a nuclear strike: land-based missiles, airdrop bombs, and submarine-launched ballistic missiles. Each method has pros and cons, but submarines are currently the most survivable. Once submerged, a submarine can lurk in any ocean for months, almost impossible to locate. Therefore, nuclear submarines carrying ballistic missiles, SSBNs, also known as strategic missile submarines, are viewed as the ultimate second strike weapon. Even if all other facilities are destroyed in a surprise attack, a hidden nuclear submarine can still launch a counterattack. This fact alone makes a preemptive nuclear strike almost impossible. But not all nuclear submarines carry nuclear weapons. Some, like attack submarines, SSNs, are mainly used to track enemy ships, gather intelligence, and launch cruise missiles. They use nuclear power to gain longer range and endurance, not to carry nuclear warheads. Regardless of the purpose, continuous presence is the core advantage of nuclear submarines. They can operate covertly near enemy coastlines, under polar ice caps, or in disputed straits. Lurking, listening, ready to act at any moment. No one knows their location. That, in itself, is a strategy. One submarine, one unknown location, is enough to keep an entire nation on alert. Thank you for watching. See you in the next video.